Hi there, this is Richard Walker from Lucidate. Welcome to the second edition in this video series on GPT-3. GPT-3 is a type of AI called a transformer. What are transformers? Transformers are a type of neural network architecture that have been revolutionizing the field of natural language processing. They're particularly good at tasks such as language translation, language modeling, and text classification. In this and the next couple of videos, we'll take a close-up view of the architecture of transformers and focus on the components that deliver their impressive results. You do not need to know all of the technical details of these components to be able to use transformer models like GPT-3. However, an understanding of some of the concepts helps design better prompts to yield more optimal results. We're going to design this video series around why we need particular components in our transformer models. Language is a challenging concept for AI to master. Our AI models are implemented in computer code and understand numbers, not words. In fields like computer vision, we can easily convert an image into numerical pixel intensities. These numbers can then be fed into our models. And the same is true for electrical signals from sensors, temperature and pressure for meteorological systems, or financial data for capital market systems. So we need an effective strategy to convert our words into numbers. To be effective, we need to be mindful of three key concepts. 1. Semantics. 2. Position, both relative and absolute. 3. Relationships and attention, which is sort of the rules of grammar. Now, some of this terminology is perhaps novel, so let's explain one by one. 1. Semantics. Words have meaning. When we assign numerical values to a word, we want to encode the meaning of the word in the numbers that are assigned. The adjective green has a different meaning to the word grass. The verb grows has a different meaning to the word quickly. 2. Position. As can be seen from the various definitions of the words green, grass, grows, and quickly, the position of the word in a sentence, or the position of a word relative to other words, is crucial. The noun grass might mean a police informer, or might mean narcotics, but its position in between green and grows cements its definition as a plant. Or consider the various definitions of the word bat in these 4 sentences. Its absolute position within the sentence, and perhaps more importantly, its relative position to the other words matters. Our numerical encoding has to cater for this. 3. Relationships and attention. This is perhaps the hardest problem to crack, but it's undoubtedly where transformers excel. Indeed, they were designed for this problem in particular. Let's look at a quick example to see what we mean by relationships and attention. Here are 2 very similar sentences. The AI executed the swap because it was an effective hedge, and the AI executed the swap because it had been trained to do so. Now, let's isolate the word it in both sentences. It occurs in more or less the same absolute position and in the same relative position to both key nouns, here AI and swap, in both sentences. In the first sentence, it relates to the noun swap, yet in the second, it relates to AI. Now, we've all been taught the rules of grammar. We know about subjects and objects in a sentence. We know that the point of the first sentence is the swap being an effective hedge, a swap as opposed to a bond or a future. And we know that in the second sentence, swap is somewhat incidental. The major point here is the AI doing something clever because it's been trained to do so. So in the first sentence, the word it is paying attention to the word swap, whereas in the second sentence, it pays attention to the word AI. Even though it is the same word and in the same position relative to other words, that is not enough. There's yet another encoding that we need to deploy to capture the attention and grammatical relationships between our words. Developing this a little further, in the first sentence, the word effective attends to the word swap. It has nothing to do in this sentence with the word AI. Correspondingly, in the second sentence, the word trained attends to AI, not swap, which it is positionally closer to. To be effective, our transformer needs to encode these attending to relationships. And remember, these encodings exist purely as numbers in a matrix. The solution that the developers of transformers came up with to solve this grammatical attention, simply using numbers in matrices, is truly mind-blowing in its elegance. But we're not going to talk about it anymore, at least not in this video, nor in the next. For the remainder of this video, we're going to talk about the first concept, semantics, and in the next video, talk about position. Once we've covered both those topics, then we'll talk about attention. If we look at the architecture of transformers, we can isolate where the different pieces of functionality live. We'll talk a little bit more about the overall transformer architecture as we go, but for our three concepts of semantics, position, and attention, we can point out the areas of our AI brain where the magic happens. Semantics, which is what we will address for the remainder of this video, lives here, while position, the subject of the next video, lives here, meaning that pretty much the rest of the transformer system is given over to attention and grammar. And again, we'll come to that in a couple of videos. So, on to semantics. How should we convert our words to numbers? One way might be to consult a dictionary and assign an integer to each word in order. This will uniquely identify each word, which is not a bad start, but it doesn't confer any meaning in the word. Furthermore, the assigned numbers will have significance. When we start multiplying and adding matrices, these numbers will matter, as we shall see in a couple of minutes. This would mean if we adopted this coding scheme, then an abacus would be worth 2 aardvarks, or if we subtract a from abacus, we get abac. As we shall see, the numeric assignments to the numbers really matter. It's how we get all of our linguistic functionality. So this simple scheme will not work. A better approach would be to use one-hot vectors. There's a link in the description if you're unfamiliar with this approach. This means words are unique and that there's no implied order or rank between the words. But as with the integer encoding, this method doesn't contain any semantics. Nevertheless, this is a good beginning, and we'll return to one-hot encoding to help us shortly. If we want to understand the meaning of a word, then we can get context from the words around it. There's a famous quote from a Cambridge professor and linguist, John Firth, who said, "You shall know a word by the company it keeps." If we wanted to predict the next word in a sentence, then we know that some words are more likely than others. If our sentence began, "The car was," then words like thatched, queen, and hat stand are unlikely candidates for the next word, while others like green, fast, stolen, and very are far more likely. The good news for language data is that there's no shortage of it on the internet, and the amount of it is growing bigger every day. At the time of writing, There were over 4 billion words on Wikipedia alone, and over 6.5 million articles. Unless Jimmy Wales has completely failed in his plea to get folks to spend £2, $2 or €2, there'll be a few more words and articles by the time you're viewing this. Big tech companies additionally have access to the content of emails, texts and tweets. We will not run out of words with which to train our models anytime soon. This means we have enough data to train some AI algorithm to predict the next word in the sentence that begins "the car was." Interestingly, when I posed this question to ChatGPT, it went a bit Marvin the Paranoid Android from Hitchhiker's Guide to the Galaxy on me. It gave me the impression that it thought I was a fool, very perspicacious of it as it turns out, and that this question was frankly beneath it. Nevertheless, before informing me that it had a pain in all the diodes down its left side, it did venture that parked, old, red, fast and clean were likely candidates, though I can confirm that none of the last three apply to my car. Predicting information from one word to the next word ahead is perhaps an okay start, but as we have so much language data, our ambitions can perhaps be set a little higher. John Firth spoke about the company a word keeps. What if we look at the likelihood of a target word appearing based not just on the preceding word, but on a whole bunch of words around it? Here's the idea. We have a target word, here boxed in red, along with some preceding and following words boxed in green. Our target word here is 5. Our goal is to predict this red word, given the green words. Now, there are lots of AI techniques we could use for this prediction, but this is a task really suited to neural networks. A link in the description will get you started if you're unfamiliar with this approach. So let's build a neural network and get it to predict a target word from a series of preceding and following words from a corpus of text. We'll first go back to one hot encoding for all the words in our vocabulary. If we first build a simple network just to predict the next word from a single word, again, not terrible, but not that reliable, kind of like predictive text on a phone, then our network would have the architecture as you see on the screen. We have an input layer and an output layer that have as many neurons as we have words in our vocabulary. For a large language model, this will be tens of thousands. Our hidden layer will be much smaller, typically a few hundred neurons. To train it, we'll take an input word from our sentence. Let's say in this case it's Mercedes, and we want it to predict the next word, which is cars. For a randomly initialized network, the initial estimate will likely be way off. As is standard for neural networks, we'll measure how badly wrong the guess was and use backpropagation to update the weights in our final hidden layer. This will result in an increase in the weights connected to our cars neuron and a decrease in the weights connected to all the other neurons. In turn, this will require a change to activations in our hidden layer. The backpropagation algorithm will relentlessly translate this into nudges and tweaks in the weights connecting our hidden layer back to our input neurons. Now, a single word predicting a single word ahead, as we said, is probably not going to yield a great result. As we discussed earlier, we can set our ambitions higher, and we'll include a bunch of preceding words and following words to get a more representative result. So here we'll scale up our input layer so that we can input more words to provide a better context. And we run this over and over and over again on our corpus of text. We can slide our window so that we get a different target word and different input words each time. Similar words from similar sentences will be surrounded by similar preceding and following words. The backpropagation algorithm will relentlessly nudge and tweak the weights and biases. Eventually, backpropagation will force a convergence in the weights and biases, and the updates to the neural network will be negligible. Once this happens, the network is said to be trained. At this point, something remarkable happens. The weights connecting the input neurons to the hidden layer will contain an encoding of that word. Similar words will have similar encodings. For instance, if this is the neuron representing the word red, it will have a set of weights connecting it to the hidden layer. And likewise, if this input neuron represents yellow, it will have its own set of weights. The weights for red and the weights for yellow will be very, very similar. Why is this? Well, as Firth said, we will judge a word by the company it keeps. Red will appear many times surrounded by the same words as yellow. The weights, of course, won't be identical. We'd expect red to be more closely associated with words like blood and devil, while yellow will have close associations with words like banana and lemon, at least as far as the ever increasingly passive-aggressive ChatGPT is concerned. So, rather than encoding our words with a single integer or a very large and very sparse one-hot encoded vector, we instead encode our words with a large, dense vector, as you can see on the screen. So, is all this complex and compute-heavy work to convert some ASCII characters into a 300-element vector worth it? Well, I think the answer is yes, and I hope you agree with me. To show you why the result is remarkable and worthwhile, let's look at what we can do with these word vectors. We can't display a 300-element vector on a chart on a screen, so I'll stick to 3D to give you a stylized view of what's going on. Let's consider 3 word vectors, one for the word king, the next for the word man, and finally the vector representation of the word woman. If we subtract the vector representing man from the vector for king and then add the encoded vector for the word woman, then the result, remarkably, is the word queen. Let's experiment further and see if the semantic relationship is preserved with other words. In addition to king and queen, we'll look at 10 other semantic relationships as per the table on the screen. The first 2 will test the logical relationships between family members, and the following 3 will use male and female as well as generational relationships from the animal kingdom. We'll then look at a couple of word analogies. These are the types of questions you sometimes see on IQ tests. In this case, we are asking what word has the same relationship to hilarious as warm has to hot, that is to say, a word meaning slightly hilarious. A perhaps harder test is the second of these questions, where we're probing the relationship between a nuclear family and an extended family. Then we have a question based on geography, and finally a couple of maths questions. How does the word encoding do on these set of tests? For our first test, we can confirm that queen is indeed the resulting word when we subtract man from king and add woman. We get a high similarity score of approximately 77%. Likewise, when we subtract father and add son, we get the expected word prince. And this semantic relationship is maintained when we go up a generation and subtract grandfather and add father. If we then look at animal relationships and subtract the masculine bull from king and add the feminine cow, we get the expected word queen, but with a lower similarity score than when we subtracted man and added woman. This is repeated when we add puppy and subtract dog. We get the expected word prince, though again with a lower similarity score. And with other words, some of them which look like the names of Saxon kings, also quite close in similarity. We get our first failure when we subtract butterfly and add caterpillar. While these words definitely have a generational relationship to each other, they also have many other meanings. A butterfly option, a butterfly stitch, butterfly stroke. They're all uses, valid uses, of the word butterfly. Caterpillar tracks and the engineering company Caterpillar stretch the meaning of this word in different directions in our 300-dimensional word embedding space. And this is perhaps our first clue that we need other encodings, such as position and attention, if we're to develop an effective language model. Our first word analogy puzzle is past. There are many other words that are also close to our target word similarity, with most of them, though not all, being very suitable alternatives to the word funny. We get our second failure with the more difficult word analogy. Our target for cousin doesn't even appear in the top 10. With that said, the embedding vector does seem to have picked up that there is something about families in the relationship between nuclear and extended, which is encouraging. But we must mark this as a fail. The next question, this time about geographical relationships, sees our encoding on much firmer footing. Paris has both a high absolute similarity as well as a high relative similarity to the other candidates. An A star here for geography. What about mathematics? With the questions posed as words or numbers, it does appear that there is some learned mathematical relationship. It turns out that this doesn't scale much beyond single numbers, but there are enough introductory mathematical texts that have been used in training to allow the encoding to have learnt simple arithmetic on a limited number set. So we've covered much in this somewhat lengthy video. Many thanks for staying with me this far. We've begun to look at the transformer architecture. Transformers are a type of neural network that are used in natural language processing tasks like language translation, language modelling and text classification. They convert words into numerical values, which is necessary for our AI to understand language. There are three key concepts to consider when encoding words numerically: semantics, that is meaning, position, both relative and absolute, and relationships and attention, which are kind of grammatical constructs. Transformers excel at capturing relationships and attention, or the way words relate to and pay attention to each other in a sentence. They do this using an attention mechanism, which allows the model to selectively focus on certain parts of the input while processing it. In the next but one video, we will look at the attention mechanism in much more detail. We can encode word semantics using a neural network to predict a target word based on a series of surrounding words in a corpus of text. The network is trained using backpropagation, adjusting the weights and biases of the input and hidden layers until all the updates become negligible and the network is said to be trained. The weights connecting the input neurons to the hidden layer will then contain an encoding of the word, with similar words having similar encodings. This allows for more efficient processing and a better understanding of the meaning and context of words in the language model. This is Richard Walker at Elucidate. Many thanks for watching. Please join me in the next video where we will discuss positional encodings.